You have probably heard that the observable universe is about 93 billion light-years across. But think about what that statement really means. No one has ever stretched a tape measure across the cosmos. No spacecraft has flown to the edge of the universe and reported back. So how can anyone claim to know its size? The answer is both simple and astonishing. We never measure the universe directly. We build a ladder. Every rung on that ladder reaches a little farther than the last. One method measures nearby stars. That measurement calibrates another method that reaches distant galaxies. Those galaxies calibrate an even larger ruler that stretches across billions of light years. Remove just one rung, and everything above it begins to wobble. Today, we're going to climb that cosmic distance ladder step by step and discover how humanity learned to measure something so unimaginably vast that light itself needs billions of years to cross it. Segment 1. The Impossible Ruler. Imagine someone asks you to measure the height of a mountain standing only a few hundred meters away. Easy enough. You could use a laser rangefinder or even walk to its base with surveying equipment. Now imagine the same person points to the moon. Your measuring tape is suddenly useless. Point to Jupiter, now the nearest star, now a galaxy millions of light years away. The problem isn't simply that these objects are far away. It's that space offers no reference points. There are no giant rulers floating between stars. There are no distance markers attached to galaxies. The universe is almost completely empty, making every object appear as if it's hanging on a black canvas with no obvious sense of depth. Your own eyes reveal this limitation every single day. Hold one finger in front of your face and close your left eye, then switch to your right eye. Your finger appears to jump against the background, but the mountains outside your window barely move at all. That tiny shift is one of the oldest measuring tools in existence. Your brain constantly converts that shift into distance without you ever realizing it. Astronomers simply expanded the same trick to the stars, but there was a problem. Even the nearest stars barely move. The shift is so unbelievably small that for thousands of years people couldn't detect it at all. Many philosophers even argued that Earth must be standing still because the stars never changed position. The stars weren't refusing to move. We simply didn't have instruments precise enough to notice. Everything changed once telescopes became accurate enough to detect movements smaller than a single arcsecond. And that unlocked the very first rung of the cosmic distance ladder. Segment 2. Nature's built-in geometry. Imagine drawing a giant triangle across space. One corner is Earth in January. Another corner is Earth 6 months later after traveling halfway around the Sun. The third corner is a nearby star. That baseline, nearly 300 million kilometers wide, becomes an enormous measuring stick. As Earth orbits the Sun, nearby stars appear to shift ever so slightly compared to stars much farther away. This tiny apparent movement is called parallax. Nothing is actually moving across the sky. It's your point of view that's changing. Think about watching a nearby tree through the window of a moving train. The tree seems to race across your view, while distant mountains barely appear to move at all. The exact same illusion happens in space, except instead of a train, Earth is racing around the Sun at roughly 30 kilometers every second. And instead of trees, we're measuring stars. The closer the star, the larger the apparent shift. The farther away it is, the smaller the angle becomes. Eventually, astronomers discovered something remarkable. Distance could be calculated entirely from geometry. No guessing. No assumptions about brightness. No estimates. Just angles and mathematics. Modern missions like Gaia have pushed this technique to extraordinary precision, mapping the positions and distances of well over 1 billion stars throughout our region of the Milky Way. For nearby stars, parallax is astonishingly reliable, but eventually the angles become too tiny. Imagine trying to detect whether a coin moved by the width of a single atom from thousands of kilometers away. That's the challenge astronomers eventually face. Beyond a certain distance, geometry alone stops working. The first ruler reaches its limit, so humanity needed another one. Segment 3. Stars that pulse like cosmic heartbeats. Suppose someone handed you 2 identical light bulbs. One sits 10 meters away. The other sits 100 meters away. Which one appears brighter? Obviously, the closer bulb. Now imagine you somehow knew the true brightness of every light bulb before turning it on. Suddenly, distance becomes easy. Compare how bright it should appear with how bright it actually appears. The difference reveals how far away it must be. Nature unexpectedly provides exactly these kinds of cosmic light bulbs. They're called Cepheid variable stars. Unlike our sun, Cepheids don't shine steadily. They rhythmically expand and contract. As they grow larger, they become brighter. As they shrink, they dim again. Over and over. Like a perfectly repeating heartbeat. For years, astronomers simply admired this strange behavior. Then they noticed something extraordinary. The slower a Cepheid pulses, the brighter it truly is. Its rhythm reveals its real power. Imagine hearing a distant lighthouse horn. Without seeing the lighthouse itself, you somehow know exactly how powerful its light must be, simply by listening to the timing of its signal. That's essentially what astronomers discovered. The pulse became an instruction manual. Measure the period, calculate the true brightness, compare it with what arrives at Earth. The distance appears almost automatically. This breakthrough transformed astronomy forever. For the first time, humanity could leap far beyond nearby stars. Cepheid variables became bridges connecting entire galaxies. They allowed astronomers to measure distances millions of light years away, and one observation changed our understanding of reality forever. When Edwin Hubble identified Cepheid stars inside what people thought was merely another cloud within the Milky Way, the calculated distance was shocking. It wasn't inside our galaxy at all. It was an entirely separate galaxy. The universe instantly became far larger than anyone had imagined, and yet even galaxies eventually became too distant for Cepheid stars to remain visible. The latter needed another rung. Segment 4. The explosions that became universal measuring sticks. Imagine standing on a coastline at night, watching dozens of lighthouses scattered across the horizon. Some appear dazzling, others are barely visible. Without knowing how powerful each lighthouse really is, you could never tell whether a dim light is far away or simply weak. Now imagine every lighthouse was built from exactly the same blueprint. The brightest beam would always have the same power. Suddenly, every lighthouse becomes a ruler. That is exactly what astronomers searched for after Cepheid stars reached their limit. The universe answered with something far more dramatic: a dying star. Not every stellar explosion is the same. Most supernovae vary wildly in brightness, but one particular kind behaves with astonishing consistency. Type Ia supernovae. These explosions begin with a white dwarf, the dense core left behind after a sun-like star reaches the end of its life. On its own, a white dwarf is stable, but if it has a nearby companion, gravity slowly steals material from the neighboring star. Imagine filling a balloon with water. At first, everything seems perfectly normal. The balloon stretches, pressure builds, nothing happens, until one final drop. The entire balloon bursts. A white dwarf behaves in a surprisingly similar way. As more material accumulates, its mass approaches a critical limit. Beyond that point, the pressure inside becomes so extreme that carbon atoms ignite almost simultaneously throughout the star. Within seconds, the white dwarf is completely destroyed. The explosion releases more energy than billions of suns combined, briefly allowing a single dying star to outshine an entire galaxy. More importantly, these explosions reach nearly the same intrinsic brightness every time. Nature has given astronomers another standard candle, the brightest one yet. If a Type 1Yes supernova appears faint, it isn't because the explosion was weak. It's because it is unimaginably far away. By comparing its known luminosity with the light arriving at Earth, astronomers can calculate distances across hundreds of millions and eventually billions of light years. Suddenly, galaxies that once seemed unreachable became measurable. The cosmic distance ladder had climbed another enormous step, but something strange appeared. The farther the galaxies were, the stranger their light became. And that strange light revealed that the universe itself was doing something no one had expected. Segment 5. When light changes its color. Think about the sound of an ambulance racing toward you. As it approaches, the siren sounds higher. The instant it passes, the pitch suddenly drops lower. Nothing about the siren actually changed. Only the motion between you and the ambulance. This phenomenon is known as the Doppler effect. Light behaves in much the same way. Instead of changing pitch, it changes color. Visible light is made of different wavelengths. Short wavelengths appear blue, long wavelengths appear red. If an object moves toward you, its light shifts slightly toward the blue end of the spectrum. If it moves away, its light stretches toward red. Astronomers call this redshift. At first, scientists expected galaxies to move randomly, some toward us, some away. Instead, they discovered an astonishing pattern. Almost every distant galaxy was shifting toward red. Nearly everything was moving away. Even more surprising, the farther a galaxy was, the greater its redshift became. It looked almost as if every galaxy in the universe had decided to flee from us at once. For a brief moment, that seemed like a reasonable conclusion. Until scientists realized something much stranger. We are not the center. Every galaxy observes almost exactly the same pattern. So what is really happening? Imagine drawing tiny dots across the surface of an uninflated balloon. Now begin inflating it. None of the dots are crawling across the rubber. Instead, the rubber itself is stretching. As the balloon grows, every dot moves farther from every other dot. No single dot sits at the center of the expansion. The surface itself is expanding. According to modern cosmology, space behaves in a remarkably similar way. Galaxies are not simply flying through empty space. The fabric of space between them is stretching. As that happens, the light traveling across that expanding space stretches as well. Its wavelength becomes longer. Blue gradually shifts toward red. Redshift is not merely evidence that galaxies are moving. It is evidence that space itself is changing while the light is in transit. That realization completely transformed our understanding of the cosmos. Because if the expansion follows consistent mathematical rules, then redshift itself becomes another ruler, one capable of measuring distances far beyond the reach of any star. Segment 6. Measuring the expansion of everything. Imagine standing beside a river. Small leaves floating nearby drift slowly. Leaves much farther downstream appear to move away faster because more water lies between you and them. Now replace the river with space itself. Every billion light years of expanding space adds a little more stretching, a little more separation, a little more redshift. This relationship became known as Hubble's law. Instead of measuring physical distance directly, astronomers measure how much a galaxy's light has stretched during its journey across the expanding universe. The greater the redshift, the farther away the galaxy almost certainly is. It is an extraordinary idea. We are no longer measuring objects. We are measuring the history written into their light. Every photon arriving at Earth's telescopes carries a record of the expanding universe it crossed. Light itself becomes the messenger. And telescopes become historians, reading a story billions of years old. The cosmic distance ladder has now grown from simple geometry to pulsating stars, to exploding white dwarfs, and finally to the expansion of space itself. Each rung depends on the accuracy of the one below it. Like constructing the tallest building on Earth, the upper floors remain trustworthy only because the foundation underneath is solid. But even after climbing every rung humanity has built, one enormous mystery still remains. How big is the universe, really? Segment 7. The number that confuses everyone. By now, you might think we've solved the mystery. We have a ladder. We have rulers. We have mathematics. So the universe must have a final size. Not quite. If you've ever searched online, you've probably seen one number repeated everywhere. 93 billion light years. People often call this the size of the universe, but that isn't actually true. It is the diameter of the observable universe. Those two ideas sound almost identical. They are not. Imagine standing alone in the middle of a vast forest at night. You carry a flashlight. No matter how powerful it is, the beam only reaches so far before darkness swallows the rest. Does that mean the forest ends where your light stops? Of course not. You've simply reached the limit of what you can see. The observable universe works in much the same way. The speed of light is incredibly fast, about 300,000 kilometers every second, but it is still finite. Every beam of light needs time to travel. When you look at the moon, you see it as it was about 1 second ago. Look at the sun. You're seeing sunlight that left roughly 8 minutes earlier. The nearest large galaxy appears as it existed millions of years ago. The deepest galaxies captured by modern space telescopes are being seen as they were more than 13 billion years in the past. Astronomy is unlike any other science. Every telescope is also a time machine. The farther you look into space, the farther you look back through time. That creates an invisible horizon. If light from an object hasn't had enough time to reach Earth since the beginning of cosmic history, then that object remains forever beyond today's observable universe. It may exist, it may not. Its light simply hasn't arrived. And perhaps never will. So why isn't the observable universe only 27.6 billion light-years across? After all, if the universe is about 13.8 billion years old, shouldn't light have traveled only 13.8 billion light-years in each direction? That question puzzled scientists for decades. The answer lies in something we've already encountered. Space itself never stopped expanding. Imagine drawing two dots on a giant rubber band. Now slowly stretch the band while a tiny ant walks from one dot toward the other. The ant keeps moving forward, but the destination is moving away at the same time. By the time the ant finally arrives, the distance between the dots has become far greater than when it began. Light experiences the same challenge. While photons travel toward us at the speed of light, the universe itself continues expanding underneath them. The galaxies that emitted that ancient light are no longer where they once were. They have been carried much farther away by the expansion of space. That is why the observable universe today measures roughly 93 billion light-years across, even though its oldest observable light has traveled for about 13.8 billion years. The number isn't describing how far light traveled through static space, it's describing where those distant regions are now. Segment 8. The edge we may never reach. Now imagine climbing the tallest mountain on Earth. After hours of climbing, you finally reach the summit. The view is breathtaking. You can see farther than ever before, yet the horizon still surrounds you. Walk farther. The horizon moves with you. You never actually reach it. The observable universe behaves in a remarkably similar way. As time passes, more ancient light has time to arrive. Our observable horizon slowly grows, but new regions remain beyond it, like chasing the horizon itself. There is another twist. Some galaxies are now so distant that the expansion of space carries them away faster than their light can ever close the gap. This does not mean they are breaking the cosmic speed limit. Nothing is racing through space faster than light in its own local neighborhood. Instead, more space is continuously appearing between us and those galaxies as the universe expands. Their future light will never reach Earth. One day, unimaginably far in the future, observers inside our own galaxy may no longer see evidence of most other galaxies at all. The expanding universe will have carried them permanently beyond view. The greatest cosmic library imaginable will slowly lose its oldest books. Page by page, light by light. That realization changes what astronomy truly is. Astronomers are not simply mapping space. They are preserving a disappearing archive of cosmic history while it is still visible. Every observation becomes precious, because tomorrow's universe may reveal slightly less than today's. Segment 9. Measuring the unknown. Let's return to the question we started with. How do we measure how big the universe is? The surprising answer is that we don't. At least, not completely. We measure the part that light has allowed us to explore. We build one ruler from geometry, another from pulsating stars, another from stellar explosions, another from the expansion of space itself. Together, those rulers form the cosmic distance ladder, one of the greatest scientific achievements in human history, yet every rung ultimately measures only the observable universe. Beyond that cosmic horizon, the story becomes uncertain. The universe could end just beyond what we can see. It could continue for trillions of light years. It could even be infinite. Current observations do not allow us to distinguish between those possibilities with certainty. And perhaps that is the most beautiful part of the entire journey. Science is often mistaken for a collection of answers. In reality, it is a method for discovering where our certainty ends. Every generation extends the ladder a little higher. Every new telescope reaches a little farther. Every improved measurement sharpens the picture of our cosmic neighborhood, but each discovery also reveals an even larger frontier waiting beyond it. So the next time you hear someone say that the universe is 93 billion light years across, remember what that number truly represents. It is not the size of everything, it is the size of everything that has had enough time to introduce itself. Beyond that horizon may lie more galaxies than we can imagine, more history than we can ever witness. Perhaps even an endless universe that no civilization will completely measure. And somehow, that doesn't make our place in the cosmos feel smaller. It makes the act of understanding it infinitely more extraordinary.